Hello, STT 315. This is recitation 6. Let's get started. So first we're going to go over some basic definitions. So we have that a probability distribution is all the possible values that the random variable can take and their probabilities P of X. Valid probability distribution must satisfy that the sum of our probabilities over X equals 1, meaning when you add up our probabilities, it should equal exactly 1, and then that our probability of X is greater than or equal to 0 for all X. So in other words, we will never have a negative probability for of X occurring. And then we have the expected value, which is mu, and that's the sum of X times P of X over our X's. And then we have the variance sigma squared, which equals the expectation of X minus mu squared, which equals X minus mu squared times P of X, and the sum of that over our X's. And then our standard deviation is the square root of our variance. The binomial distribution. So imagine that you repeat identical random experiments or trials, each with two possible outcomes. You either have success or failure exactly n times, where the probability of success is P and the probability of failure is 1 minus P. Moreover, suppose that the experiments are independent. If the random variable X represents the number of successes in n trials, we say it follows the binomial distribution, with the number of trials n and the probability of success P. In this case, we have the probability of X equals equals the sum of n choose X times P to the X times 1 minus P to the n minus X, where our sum is over from X equals 0 to n. So a basic example of what would follow a binomial distribution would be a coin toss, where you either get heads or tails, where we can say that if we're interested in the number of heads we get, we could say a success would be we get a head, a failure would be that we get a tail, and n would be the number of times we do the coin flip, and each coin flip is independent because it doesn't depend. If I do 3 coin flips, the second coin flip doesn't depend on the first coin flip, and the third coin flip doesn't depend on the 2 previous coin flips, so they're independent trials. Okay, so question 1, a discrete random variable can assume 5 possible values, 2, 3, 5, 8, and 10. Its probability distribution as follows. I know it's a little blurry, but we have our X can take 2, 3, 5, 10, 5, 8, and 10, which is the first row. And then we have our probability of X being the second row. So the probability of X equal 2 would be 0.15. The probability of X being 3 would be 0.10. The probability of X being 5, we don't know that. We're not given that. The probability of X equal 8 would be 0.25, and the probability of X being 10 is 0.25. So this is all given to us. And we want to know what is the probability that our X equals 5. So we want to find this unknown probability. So we know that we were told that this is a probability distribution, and we know that a valid probability distribution must satisfy that the sum of our probabilities over all of our X's should equal 1, and that each probability will be greater than or equal to 0. So notice that so far, these are all of the probabilities we're given are non-negative. So they're either 0 or greater than 0. We don't have any equaling 0. And we should know that all of these plus this unknown one should equal 1. So what we can do is just set up a simple algebraic equation, because we know that our sum of the probability should equal 1. So we can take 0.15 plus 0.10 plus this probability of x equal 5, and then plus 0.25 plus 0.25 equal 1. So when we add up all of the numbers we are given, we're given it equals 0.75. So we have probability of x equal 5 plus 0.75 equals 1. So if we solve for probability of x equals 5, we're going to subtract the 0.75 on both sides, and then we'll get that a probability of x equals 5 is 0.25. And I probably should have written probability of x equals 5. So this is like my own shorthand, so it's not totally, I don't know, proper, I guess. But anyways, this is the probability of x equals 5. What is the probability that x equals 2 or 10? So the probability of x equals 2 or 10 equals the probability of x equals 2 union the probability of x equals 10. And I like to think of unions as like a, or, where intersections are and. So we're in an or situation, so we have a union. And so that's going to equal the probability of x equals 2 plus the probability of x equals 10. And so we're given these probabilities. So we have the probability of x equals 2 equals 0.15. And then for x equals 10 is 0.25. So you add those two probabilities together, and that gives you 0.4. Next is the probability that x is less than or equal to 8. So there's two ways to think about this. First is like the more efficient way. So we can do 1 minus the probability that x equals 10. The reason being is we can take 1 minus the complement of x less than or equal to 8. So the complement of x less than or equal to 8 would be x greater than 8. So it would be 1 minus the probability of x greater than 8. And so if we look at our x's that are greater than 8, we're only in the situation where x equals 10. So I kind of skipped a step in writing. So we have 1 minus the probability that x equals 10, and we're given that that probability is 0.25 for the probability that x equals 10. So we'll do 1 minus 0.25, and that'll give us 0.75. So that's the more efficient way of solving it. Or we can just do it in a more straightforward way, even though it's more calculation. So the probability that x is less than or equal to 8. So we can add up all the probabilities. So like the probability for x equals 2, x equals 3, x equals 5, and x equals 8. So when we add up those 4 probabilities, we also get 0.75. So I just wanted to do it both ways to show you that this way is obviously more efficient, but there is, more than one way to solve this question. What value of x is most probable? So if we look at our different probabilities in here, don't forget the probability of x equals 5 is 0.25, which we found here. So if we want to see what's more probable, we're going to see where is our probability of x the highest. And so we have 5, 8, and 10 all have the probability of occurring at point, our probability of x is 0.25 for all 3 of these values. So those would be the most probable of occurring. They're more likely to occur than 2 and 3. So our answer is 5, 8, and 10. Next, we want to display the probability distribution as a graph. So we're going to have our values of x, the values x can take, so 2, 3, 5, 8, and 10 on the x-axis. And then we have our y-axis be the probabilities. So I'm just going to, so like when I went to see, okay, how far the bar will go for 2, I'm going to scroll up, see, okay, the probability of x equals 2 is 0.15. So 0.15 would be the height of 2. And then the probability of x equals 3 is 0.1. The probability of x equals 5 is 0.25. And then same for 8 and 10. So the x's are on the x-axis, and then our probabilities of x occurring are on the y-axis. Next, we're going to want to find the expectation of x. So here we were given the expected value here, which is the sum over our x's of x times p of x. So when we do that, here we have, so the sum of xi times p of x equal xi, and here we have our x's are, we have from I equal 1 to 5, because we have 1, 2, 3, 4, 5, like different x's it's going to go through. So when we do that, we're going to take, okay, so, and I'm just going to use the graph so I don't keep scrolling up, but you can either look at the table or the graph that you just made or we made. So we have, first let's do where I equals 1. So we have x1 equals 2, and then we have the probability of x equaling 2 is 0.15. And then we're going to add that to the probability of 3 times 0.10, which is our probability of 3 occurring. And then we're going to add that to our next like x value. So x equals 5. So we have 5 times 0.25. And then we're going to add that to 8 times 0.25. And then we're going to add that to 10 times 0.25. So when you put that in your calculator, you should get 6.35 as our expectation of x. All right. Next is, what is the probability that x is greater than 2? So we can do this in 2 different ways again. So we can either do like the more efficient way. So the probability of x greater than 2 would be 1 minus the complement of x greater than 2. So the complement of that would be that x is less than or equal to 2. So 1 minus the probability of x is less than or equal to 2. Well, our lowest value that x can take is 2. So we don't have any, x can't take value 1 or 0 or a negative value in the probability distribution that we're given. So we're just going to do 1 minus the probability that x equals 2, which is 0.15. So 1 minus 0.15 is 0.85. And then we have the probability that x is greater than 2. So we can solve this looking at, okay, well, the probability that x is greater than 2 would be the probability that x equals 3 plus the probability that x equals 5 plus the probability that x equals 8 plus the probability that x equals 10. So when you add up those probabilities, that would be 0.10 plus 0.25 plus 0.25 plus 0.25, you'll get 0.85. So you'll get the same thing. So it's just which way you want to look at it. But the left-hand side method is more efficient. So I would definitely try to get comfortable doing that by the time you have an exam. But understanding both is important. All right, so question 2. Explain why each of the following is or is not a valid probability distribution of a discrete random variable x. So remember to keep in mind, what does a valid probability distribution satisfy? So that when you add up all the probabilities over x, you'll get 1, and that each probability is greater than or equal to 0. So we're going to hold on to that when we're solving question 2. So first, and I wrote those two properties here. So we're given this. So let's first add up all of our probabilities to see if they equal 1. So when you add 0.1 plus 0.3 plus 0.3 plus 0.2, you get 0.9, which does not equal 1. So it doesn't satisfy that first condition where they all have to equal 1. So it's not a valid probability distribution. Next, we're going to check two things. So first, we're going to add up the probabilities. So 0.25 plus 0.5 plus 0.25 is 1. And then we also have all of these probabilities are greater than or equal to 0. We don't have any negative probabilities. So 0.25 is non-negative, 0.5 is non-negative, and 0.25 is non-negative. So we're good here. So this is a valid probability distribution. Here, well, if you add them together, you'll get that they don't equal 1, but also notice that here we have a negative probability for x equals 4, and that you can't have a negative probability. So that's not a valid probability distribution. So there should be a red X there. Next, let's add up these probabilities. So we'll get 1.1 when we do, which does not equal 1. So that's incorrect. And that's it for question 2. Now on to question 3. So consider the probability distribution for the random variable x shown here. So we have the probability of x equals 10 is 0.05, and so on and so forth. And now we want to find mu, sigma, and sigma squared. So remember, in case if you forget, we have those definitions here. So mu is the expected value, variance is sigma squared, and standard deviation is sigma. So we want to find those three values for this probability distribution. So notice here too, if you wanted to check that it's a valid probability distribution, notice that all of these probabilities are greater than or equal to 0. We don't have any negative probabilities. And then if you were to add up all of these in the second row, that they would all be, that they would equal 1. So first, let's find what mu is, the expected value. So we can take the sum from I equal 1, 2, 3, 4, 5, 6 times, okay, so the sum of xi times the probability of x equals xi. So we're going to take 10 times 0.05, then plus 20 times 0.2, plus 30 times 0.3, plus 40 times 0.25, plus 50 times 0.1, plus 60 times 0.1. So when you solve that and punch it in your calculator, if you do, you have to do multiplication first. So then you'll get the second row, and then when you add those together, you should get 34.5 as our expected value mu. Next, we have, we're going to find our sigma squared, our variance. So as given earlier in our definitions at the beginning of this recitation, it equals the sum of xi minus mu squared times the probability of x equal xi. So we're going to use the mu that we just found in the yellow box. So we're going to take, so let's say for I equals 1, we're going to take have our x1 be 10. So we're going to have 10 minus mu, which is 34.5 squared, and then times the probability that x equals 10, which is 0.05. And then we're going to do that for every single x. So then next we have 20 minus, our mu is going to stay the same throughout all of this process. So 20 minus 34.5 squared times 0.2 plus 30 minus 34.5 squared times 0.3, and then 40 minus 34.5 squared times 0.25, plus 50 minus 34.5 squared times 0.1, and then plus 60 minus our mean squared times 0.1. So if I wanted to show my work step by step, I first would do what's in the parentheses. So that would be our x values minusing our mean. So I get this, and then I would square them and then multiply by our different probabilities that we have. So when you go through and do all of that work, you should get 174.75 as our variance. And then we want to find our standard deviation next. So that equals the square root of our variance. So we're going to take the square root of our 174.75, and then we'll get 13.219 as our standard deviation. So that concludes question 3A. And then next we want to graph P of X. So we have that on our y-axis, and we have our x's on our x-axis. So we have that x can take value 10, 20, 30, 40, 50, 60. And then we'll have our probabilities here. So when I go through and do it, first let's do 10. So the probability that x equals 10 is 0.05. So that will be the height of that bar. And then we have 20. The probability x equals 20 is 0.2. So that would be here. And then the probability that x equals 30 is 0.3. The probability that x equals 40 is 0.2. Sorry, did I say 30? The probability x equals 40 is 0.25. And then the probability of x equals 50 is 0.1. And then the probability that x equals 60 is 0.1. So you'll get a graph that looks something like that. And notice that that our mean is 34.5. So that's somewhere in here, which is what you would expect. And yep, our variance and standard deviation is also what you would expect looking at the graph. Okay. Next is question 4. In a Pew Research Center survey titled U.S. Smartphone Use in 2016, more than 2,000 smartphone users were asked how often the apps they downloaded on their phones were not working correctly. Responses were recorded as follows. 1 is frequently, 2 occasionally, 3 would be rarely, and 4 would be never. The probability distribution for the numerical response X is down here. So we have the probability that like a participant would choose 1 frequently is 0.1, and so on and so forth. So we want to verify, part A is to verify the properties of a probability distribution for a discrete random variable are satisfied. So remember, we have these two properties, that the sum of our probabilities will equal 1, and that all of the probabilities are non-negative. So if we add all of these probabilities in the second column, we'll get that they do indeed equal 1. And notice that we don't have any negative probabilities. So that's good, check. So both of these are satisfied. So that means that we have a valid probability distribution. So we have verified those properties. Next is part B, so find the probability that x is greater than 2. So the probability that x is greater than 2 would be that x equals 3 and x equals 4. So if we add those two probabilities together, we get 0.51. Next, we're going to find the expectation of x and interpret the value. So the expectation of x is the sum of our xi times the probability that x equals xi. So if we go and look up here, we have 1 times 0.1 plus 2 times 0.39 plus 3 times 0.4 plus 4 times 0.11. So when we do that, we should get 2.52. So the probability distribution is centered around our expectation of x. So our probability distribution is centered around 2.52. All right, so next is question 5, a different question. So we have a poll found that 22% of US adults do not work at all while on summer vacation. And in a random sample of 10 US adults, let X represent the number who do not work during summer vacation. For this experiment, we're going to define the event that represents a success. So here we have, we're going to have X represent the number who do not work during summer vacation. So we have a success would be that a US adults not working during summer vacation would mean a success. A failure would be that the US adult does not work during does work during summer vacation. Give the value of P for this binomial experiment. So here we're given that this 22% of US adults do not work at all while on summer vacation. So that, remember, in our eyes is a success. So that probability of success we're given as 22%. And then we want to find the probability that X equals 3. So we can do that in our calculator by doing, going to your distribution function and choosing binomial PDF. And here it will have you put in your n number of your sample number. So here we have, in this situation, 10. And then we have, next it wants you to input the probability of success. So in this question, it would be 22%. And then here we want to find the probability that X equals 3. So here our X value is 3 that we're interested in. So when you put this into your calculator, it'll be 0.2244. Next, we want to find the probability that this should be that 2 or fewer of the 10 US adults do not work during the summer vacation. So here we have the probability that X is less than or equal to 2. So now we'll use binomial CDF instead of PDF. And our N, our sample size, will still be the same. It'll be 10. Our success probability is still the same because we're in the same probability distribution. And then our cutoff value is 2, which is 0.6169. And note that I tend to use the TI Inspired calculator. And on that calculator, it wants you to put in your lower bound. So when I solved it on my calculator, I had put 0 as my lower bound. Anyway, so yeah, so for both of these, you'll want to use your calculator. And also, so the difference between PDF and CDF, this is good graphs to kind of keep in mind. So the binomial PDF looks something like this. and then our binomial CDF, the ranges from 0 to 1. And so if we were to, so these are two PDF and CDF. The graphs are helpful to keep in mind to kind of keep it straight. Okay. Next I'm going to go over homework 2, the solutions to homework 2. So here okay, so one letter from the sentence I love New York is chosen in the following way. First, a word is chosen at random, and then a letter is chosen from the word. Round your answers to 3 decimal places for the questions below. So first is, what is the probability that the word love is selected? So we're gonna, our answer is 1/4 because we have, there's only one word out of these 4 words that are, that's the word love, so that's 1. And then our total possibility of words that could have been selected is 4, because there's a total of 4 words, so that's 1/4. So we get 0.25 as our answer. Next is, what is the probability that the letter E is selected? And so we have 2 possibilities, and note that the selection of a word and then a selection of the letter are independent. So we have we would have 1/4 is the selection of the word love, and then which we found from part A, and then to select E from that word would be 1/4 because only one letter is the E out of the 4 letters in that word, so that's 1/4. So we're going to multiply those together and then add that to, so let's say, what is the probability we select the word new? So that would be 1/4 again. And then we would have, what about getting that letter E out of that word new? So we would have, that would be 1/3. So when you solve this, put it in your calculator, you should get 0.146. And then next is, given that the letter E was selected, what is the probability that the word chosen was love? So here we have our keyword is given, so I know we're going to be dealing with a conditional probability. So that's a probability that we chose the word love given E is selected. So that's the probability of love intersect E divided by the probability of E. So the probability of love being chosen is 1 intersected with E is times 1/4. Sorry, so 1/4 times 1/4 is our numerator, and then our denominator is the probability that E is selected, which we found in part B, which is 0.145833. So when you solve this, you get 0.428. Okay. Next is the sample space for the response of a single person's voting preference consists of 3 elementary outcomes. So we have E1 is your Republican, E2 is your Democrat, and E3 is your independent. The probability that a single person's voting preference is Republican is 0.1. The probability that a person's voting preference is Democrat is 0.32. And we want to find the probability that a single person's voting preference is E3. So we're going to take 1 minus the values that were given. So we have 1 minus 0.1 plus 0.32, and that equals 0.58. Next is toss a coin 3 times. Let HI be the event of getting a head and TI be the TI of getting a tail at ith time for I equal 1, 2, 3. So if let's say we had H1, that means that for we got a head on the first coin toss. If we had T1, that means on the first coin toss we got a tail. So which of the following events is the event of getting at least one head in the 3 tosses? So our correct answer would be H1 union H2 union H3, because to get at least one head, that means that you would get a head in the first toss, or in the second head toss, or in the third head toss. So that's why these are all unions, because you can think of them as an or situation opposed to an and. And we wouldn't have any tails in our answer because yeah, we're interested in getting at least one head in the 3 coin tosses. All right, so the complement of getting at least one head is getting all tails. And we're going to say true or false for the following statements. So keep in mind that like H1 and T1 are disjoint, meaning in the first coin flip, you can't have a head and a tail. So they're mutually exclusive or disjoint, H1 and T1, or H2 and T2 are disjoint because for the second flip, you can't have both heads and tails, and so on and so forth. So let's keep that in mind when we go through these. So H1 and T2 are mutually exclusive. So that's false, because you can get a head for the first coin toss and a tail for the second coin toss. They're not mutually exclusive. In other words, their intersection is not the empty set. They both can happen. T1 and H2 are mutually exclusive. So that's also false, because you can get a tail for the first toss and a head for the second toss. So those are not mutually exclusive. So that would be false. H1 and H2 are mutually exclusive. That's also false, because you can get a head on the first toss and a head on the second toss. Their intersection is not the empty set. So that's false. And T1 and H2 are mutually exclusive. That's false, and that's the same thing written here. So yeah, I already explained why that's false. And then T1 union T2 and 2, 3 are mutually exclusive. That's false, because getting a tail on the first or second toss and getting a tail on the third toss, that all can happen. And yeah, so that would be false. They're not mutually exclusive. In other words, the intersection of T1 union T2 with T3 is not empty. So all of these here are false. Next, we have A and B are 2 events. Answer true or false for the following statements. There could be more than one correct statement. So here, let's say this is event A and this is event B, and note that their intersection would be A intersect B. So let's see. So this is separate from the coin toss situation. We just have event A and B and their intersection here. So A union B is a subset of A intersect B. So that's false, because A union B would be this whole blue area and this whole red area. And the intersection here is this purple area here. So to say that the blue area plus the red area is a subset of the purple area, meaning like you can fit these big areas into here, this is a subset, that's incorrect. What's true would be that A intersect B is a subset of this bigger part of the blue and the red, which is here. A intersect B is a subset of A union B. So that's what's true. This first statement here is false. Next, A is a subset of A intersect B. So that's also false because you'll notice that between all of A and then A intersect B, A intersect B is the subset of A, not the other way around. A is the larger space that contains A intersect B. So to say that A is a subset of this small region would be incorrect. So that's false. We already discussed this third one, that's true. A intersect B is a subset of A. So this smaller purple is a subset of the blue. That is correct. So this fourth statement is correct. And then next, A is a subset of A union B. So, yeah, so this blue is a subset of, the blue and the red, including the intersection. So that is true. Because A union B is all of A and all of B, including the intersection. So, yeah, A is a subset of all of that. Next, we have, I'm going to kind of zoom out so you can see my drawing at the same time. More questions that are like this. So we want to see what statements are true and what statements are false. So here, it's the same drawing as before where we have our purple area as our intersection. And here I also drew like S is our whole sample space. So the first statement, A is a subset of A union B. So that would be true. The blue area is a subset of the blue, purple, and red. So that's true. A intersect AC equals the empty set. So A is all of the blue. And A complement is all of the subspace except A. So that would be this part of the red and then all of this outside space. So if we take the intersection of A and everything that's not A, meaning, yeah, that we're gonna see what does this A have in common with everything that's not A, it would be nothing. So the intersection is the empty set. So that is correct. Next, A intersect B is a subset of A. So A intersect B is this purple area, and it is indeed a subset of this blue circle. So it's contained in that blue circle, so that's true. Next is A union B is a subset of A intersect B. So that's false because A union B is the, like larger area. There's parts of A union B that are not in A intersect B. So that's false. A intersect B is a subset of A union B. That's true. This blue purple area is contained in the blue, purple, and red area. So that's true. A union AC equals the sample space. So that's true. So if we take A, which is this blue circle, and take a union with everything else outside of that A, we will get the whole sample space. So we'll get the rest of this red alone area mixed with the rest of this area inside the box. Next is A union A complement equals the empty set. So that's false. We already said that that would be the whole sample space. If this were an intersection, then we would have the empty set, but we have a union. So we get the whole thing, the sample space. Next is A intersect A complement equals the sample space. That's false. And A is a subset of A intersect B is also false. Because, yeah, for example, this blue area is not contained in A intersect B. So that's false. Next, I'm going to zoom back in a little bit. A letter is picked from the sentence, James loves exams, by first choosing a word at random, then picking a letter from the word. Let J stand for the event the word James is picked. Let H stand for the event the letter E is picked. Then here we have that J and H are independent but not mutually exclusive. So the reason being is these two events do not depend on each other, but however, both of these events can happen. So you can choose the word James and you can choose that E is picked, but they're not, they don't depend on one another. So that's why it's independent, but they're not mutually exclusive, meaning both of these events could happen. Their intersection is not empty. All right, next is real estate ads suggest that 50% of homes for sales have garages, 10% have swimming pools, and 5% have both features. So I'm going to zoom out again so you can see the whole thing. So here I just filled in that information. So here our intersection is 5%, and then we know, okay, so 50%, which is 45 plus 5%, would be the percent of home sales that have garages, and then here 10% would be where the homes for sale have a swimming pool. So the first question, the probability that a home picked at random will have a pool or garage is, so that would be, we're going to add all these probabilities together. So 45 plus 5 plus 5 equals 55%. And then the probability that a home picked at random will have neither a pool nor a garage. So that situation would be this area outside both these circles. So remember that all of these added together should equal 1. So if I did 1 minus 45 minus 5 minus 5%, you'll get 45% out here. So that's how you get 45%, because that is where the home picked does not have a garage or a swimming pool. Okay. Next, suppose that 26% of the population in an area is exposed to a television commercial for Ford automobiles, and 46% is exposed to Ford radio advertisements. Also, 15% is exposed to both means of advertising, so both TV and radio. For a person picked at random from the population, let A stand for the event exposed to television commercial and B stand for the event radio advertisement. What is the intersection? So the intersection is 0.15. So there's really nothing to compute because it's given to you right here. So it's just being able to identify in this information what the intersection would be, which is 0.15 for where, you know, the population is exposed to both means of advertising, so both TV and radio. Next is a consulting firm is bidding for 2 jobs, one with each of 2 multinational corporations. The company executives estimate that the probability of obtaining the consulting job with firm A, event A, is 0.7. The executives also feel that the company should get the job with firm A, then there's a 0.5 probability that firm B will also give the consulting job. What is the chance of the company getting both jobs? So here we have the probability of A is 0.7. The probability of B given A is 0.5, meaning the, yep. And then here we want to find what is the chance the company, of the company getting both jobs. So that would be the intersection where they get A and B. So here, this first equation is something that was discussed last recitation. So we have this intersection equals the probability of B given A times the probability of A, and we're given these 2 values. So we're just going to plug in Chuck. So we get the conditional probability is 0.5 times 0.7, and that gives us 0.35, which is our answer. Next, a sales representative in the music section of Best Buy notes that 15% of her customers buy the Best of Nora Jones and classical guitar by John Williams. She also knows that 70% of customers buy classical guitar with John Williams. Given that one of her customers bought classical guitar by John Williams, what is the probability that the customer will also buy the Best of Nora Jones? So here, given is our keyword, and we have a conditional probability distribution. So we want to know the probability the customer will buy the Nora Jones album, given that they bought the one by John Williams. So the probability of N stands for Nora and J stands for John. So this conditional probability equals the probability of N intersect J divided by the probability of J. So this equation here was also discussed last recitation. So the probability of the intersection is 0.15 because we have 15% of our customers buy the Nora Jones and the John Williams. So that's 0.15. And then we're going to divide that by the probability of J, which is 0.7, because we have 70% of customers buy the album by John Williams. So when we compute this, we get 0.214, which is what we needed. All right, next we have, a package of documents needs to be sent to a given destination, and it is important that it arrive within 1 day. To maximize the chances of on-time delivery, 3 copies of the document are sent via 3 different services. Service A delivers the document on time with probability 0.9, Service B with probability 0.95, and Service C with probability 0.8. What is the probability that at least 1 copy of the document will be delivered on time? So here I'm going to do essentially 1 minus the complement. So the complement of at least 1 copy of the document being delivered on time is that no document will be delivered on time. So that's the complement of that situation. So the probability that no document will be delivered on time is 0.1, which is 1 minus 0.9, and then times 0.05. And I got this number by doing 1 minus 0.95. And then times 0.3, which I got by doing 1 minus the probability, or 1 minus 0.8. So when I multiply all these, I get 0.0015. But remember, this is the complement of what we're interested in. So we're going to do 1 minus the 0.0015, and that gives us 0.99, which is the probability at least 1 document is delivered on time. Next is, what is the probability that all 3 services will deliver the document on time? So here we were given, these are the probabilities that Service A will deliver on time, Service B will deliver on time, and Service C will deliver on time. So if we multiply all of those values together, we get 0.684. What is the probability of getting at least 1 6 in 3 tosses of a fair 6-sided die? So here, I'm going to zoom out so you can kind of see it all at once. So here we have 6 times 6 times 6 is 216. So that's the number of like total outcomes we can think of. So there are, because each dice or die is 6 sides. So there are 125 out of 216 chances of not getting a 6 when 3 dice are rolled, because we have, so in the first trial, if we didn't get a 6, then that means we could have a 1, 2, 3, 4, or a 5. So that's 5 options out of 6. and then our second roll would be here, and we're multiplying them all because each roll of the dice is independent. So we have the second roll would be 5 divided by 6, and then the third roll would be 5 divided by 6. So when you multiply all those together, we get 125 divided by 216. So that's the chances of not getting a 6 when 3 dice are rolled. So then if we take 216 and subtract 125, which is what we got here, that would be 91. So 91 divided by 216, our total number of outcomes, is the chance that at least 1 6 will appear when 3 dice are rolled. So so we kind of did the same situation as here, where we first found the complement and then worked from there. Next is our last question. So I'll just show you all at once. John can take one of 2 highways, Interstate A and Interstate B, to get to work each day. The probability that there will be a traffic jam on Interstate A on a given day is 0.06. The probability that there will be a traffic jam on Interstate B is 0.3. The probability that there will be a traffic jam on at least one of Interstate A or B is 0.8. So here we have the keyword was or, so that's a union situation. So the probability of A union B is 0.8. So the first question is, determine the probability that both Interstate A and Interstate B will be congested. So we have the probability of A union B equals the probability of A plus the probability of B minus the intersection. So here we have, sorry, let me just backtrack. So we want to find that both Interstate A and Interstate B will be congested. So that's an intersection situation. So our goal is to find the probability of A intersect B. So here, I'm just rearranging the equation we already have. So we have that the probability of A union B equals this, which we had learned, I believe, last recitation. So if we rearrange this and add, the probability of the intersection to both sides and then subtract the probability of the union, we get this second equation. And so then from here, we can just plug in checks. So we get the probability of A, which is 0.6, the probability of B, which is 0.3, and then the probability of the union, which is 0.8. So when you add all those together, you get 0.1. Determine the probability that Interstate B is congested given that Interstate A is congested. So here we have that word given, so the light bulb will go on that we're dealing with a conditional probability. So the probability that Interstate B is congested given Interstate A is congested. So we have the probability of B given A. And that equals the probability of A intersect B over the probability of A. This was a property that was also previously discussed. So we know the probability of A intersect B because that was what we just solved in this first problem, which is 0.1. And then the probability of A is 0.6. So then 0.1 divided by 0.6 is 0.167. And then lastly, determine the probability that there is a traffic jam on Interstate A, given that at least one of the interstates has a traffic jam. So here we have that given word again. So we have a conditional probability. So the probability of A given A union B. So that's the probability of A intersect A union B divided by the probability of A union B. So that would be 0.6 divided by 0.8. Excuse me. And that gives you 0.75. And that concludes recitation 6. Thanks.